Hello everyone, and welcome to this video on the push forward of vectors on manifolds. Now, the push forward of a vector is a fundamental concept in differential geometry, particularly when dealing with differential maps between manifolds. It provides a way to map vectors from one tangent space on a manifold to another tangent space on a different manifold, respecting the smooth structure of the manifolds and the differential map between them. So the smooth structure and the differential map will be important. In the case of a coordinate change, the two manifolds are the same, just equipped with different coordinate systems. So let's make a start, and we shall go over. All right, so just a brief summary again. Let's remind ourselves of manifolds and tangent spaces. I've covered this in previous videos, but I'm just going to briefly, for the sake of completeness here, just briefly run over it. So a manifold M is a topological space that locally resembles Euclidean space Rn, depending on what dimension you're in. At each point P belongs to M, or as an element of M, there is an associated tangent space T, the tangent space to the manifold M at the point P, which is a vector space consisting of all possible tangent vectors at P. Now, these tangent vectors can be thought of as directional derivatives of smooth functions defined on the manifold. And in this series, I've covered that in other videos and shown you how they're directional derivatives. Anyway, remind ourselves, here's a two-dimensional manifold in orange, and here at the point P, and only at the point P, we have this tangent space attached to the manifold only at point P, and then we have just some random vector V on it. So the tangent space of manifold M at the point P is the yellow flat two-dimensional R2 Euclidean space. All right, so differential maps between manifolds. Perhaps I need to get rid of that. All right, so consider two smooth manifolds, M and N, and a smooth map, a differentiable function, F, that maps M to N. Now the map F takes points on M to points on N, shown here by the red line. If P belongs to the manifold M, or M subscript P at the point P, then F of P belongs to N, right? And F is the map from M to N. So take the point P on the manifold M and substitute it into F, and we get the output, the image, the range, if you like. P is in the domain, or the pre-image. F of P is the image, or the range, or the output of this map F from M to N, F of P. And that will, of course, be important, as you'll see going along. It's the existence of this map that makes what follows in the rest of this video about the push forward of vectors possible on manifolds. All right, so M and N, let's just talk now about the manifolds M and N, just a little bit about them before we get into the task at hand. So different manifolds, typically M and N are considered different manifolds. For example, M could be a two-dimensional sphere and N could be a three-dimensional Euclidean space. In this case, F maps points from one manifold to another. They could be the same manifold. It is also possible for M and N to be the same manifold. For instance, M equals N equals R2, two-dimensional Euclidean space. Here, F is a map from a manifold to itself, often used to describe transformations or automorphisms, that is, self-maps that preserve structure. Now, there could be both scenarios. So the statement F M to N, or F is a map from N to N, is general and can cover both cases. It simply indicates a function from one space to another without specifying whether these spaces are the same or different. So F is a map from manifold M to manifold N. All right, now smooth manifolds. When we say M and N are smooth manifolds, we mean that they are manifolds equipped with a smooth structure, allowing for the definition of smooth, continuously differentiable functions between them. So there's no sharp points where the gradient suddenly changes sign, and there's no discontinuities where F is not defined. All right, so smooth, that's continuously differentiable. So we don't have, for instance, the absolute value of x in one dimension, the absolute value of x, where at x equals 0, the gradient changes sign from -1 to +1, depending if you're going left to right. So there's a sudden change at that point in gradient. We don't have that. These are smooth and continuous, so they're continuously differentiable. Now, smooth map, a differentiable function. F is a map from M to N. A map F is called smooth if in every local coordinate system on M and N, the functions representing F are infinitely differentiable. This means that F behaves nicely with respect to the smooth structures of M and N. Again, there's no sharp points or discontinuities in the gradient or discontinuities in the manifold itself. All right, so what we're interested in then, say given manifold M and the manifold N, how can we take a vector in the tangent space here? Remember, vectors exist in the tangent space of the manifold at each given point. You might have some vector field on the manifold, then at each point you'll have a vector related to that field. Let's just say it's electric field, magnetic field, whatever it is, some field. And at each point on a manifold, you'll have a tangent space at that point, and the vectors that belong to the electric field, magnetic field, whatever the vector quantity you're looking at will be in that point. And you will have this tangent space to that point, and the vectors will exist in that tangent space. So how can we relate vectors between the two tangent spaces? For instance, this vector here at P on the manifold M, in the tangent space of manifold M at the point P, how do we relate that to the vector here at F of P in the tangent space to the manifold N at the point F of P? All right, so how is a vector on TPM related to one on TF of Pn under the mapping F takes maps from M to N? And that's the point of this video. That's what we're going to get at. So, all right, let's just start talking general terms. So we have F as a map from M to N, and we let dimension of M be M and the dimension of N be N. They don't have to be the same. They don't have to both be M or both be N. They can be different. So we have the coordinates on M, okay, x1 all the way up to xm, depending on the dimension M, all right? And then we have on N, the coordinate functions, the functions of the coordinates under this mapping F. It's very important the mapping F exists, otherwise this doesn't follow. So we're mapping these points to these points. All right, and notice we have F1 of these coordinates, functions or coordinate functions here, F2 up to Fn, depending on the dimension n. Now we can find, the idea here is if we're going to relate vectors on M to vectors on N, then we're going to have to deal with the mapping. So what we want to do, what we can do, because remember how F takes points on M and gives you a corresponding point, takes the points on M as its domain and gives you points on N, F of P, whatever point is, all right, at the image, all right, then what we're going to need to have to do then is let's start in one dimension and then we'll build up. So we can find an approximation to the function f, whatever f is in however many dimensions. Let's just say here we're in f is a map from the reals to the reals in one dimension here. Here's f of x, a plot of f of x versus x. Here's our f of x. And it turns out that any given point, let's just say point P, we can find a very good linear approximation to f of x. Remember, this is the map from manifold M to manifold N. That's ultimately what we're getting at. But we can find a very good approximation to f of x at this point and close to this point. So around x equals P here, around this point P, and for small range of values either side of it, small domain either side of it, we can find a very good approximation to the function f of x. So this blue line here is our function f of x, function of one dimension, one variable, okay? But at a given point, we can find a very good linear approximation. But as we move away from the point P, like say over to x here, that approximation becomes less and less accurate, and the error, the difference between the approximation and the actual curve itself grows enormously, all right? But for a small range of values around P here, we have a very good and excellent linear fit and an exact fit at the point P itself. Now this red line here, this straight line here, is something we've learned about from school. Remember the equation of this line, straight line, is y equals mx plus c. M is the gradient, the slope of the line, c is the vertical intercept, okay? So we think of this as y equals mx plus c, or f of x equals mx plus c, okay? So we can find the equation of this line and we can center it on the point P. We want the equation of the line that passes through x equals P and f of P. All right, so through this coordinate here, all right, we can find a very good fit, a very good linear fit. And for a small range of values either side, it's still a very, very good fit. And that means that at that point, we can approximate this f of x. We can approximate it. F of x is approximately around this point for values close to P, either side of it, is d times f of P, which is the derivative of f evaluated at P, which is our m, the gradient, times x minus P, plus this bit on the end here, f of P, the point at which we've centered it. All right, so this is the equation of our straight line in red here. All right, in the case of one-dimension variable, one-dimensional function of one dimension or function of single variable. And at the point P, so this red line passes through x equals P, its y coordinates, vertical coordinates, f of P. All right. And this now, you see how it's got the function, the mapping f involved, and it's got the point P. See, all right, and that's what we're interested in. Remember on the manifold M, we had this point P and then we had a tangent space attached to the manifold at that point P only. And that's what we're interested in. So F helps us there. Now, df of P, I'm going to be getting onto the Jacobian shortly, but df of P in this case is just the derivative of F, and then it's evaluated at the point P, x equals P. All right, so just at this one point, we have an excellent approximation here. And for small values, either side of it is still an excellent approximation to f of x. Globally, of course, it's not an approximation at all. It's no way would you consider this linear fit acceptable for the rest of the globally. But just at this point P here, it's an excellent fit. All right, some notation, df dx. This is the ordinary derivative evaluated at the point P. So df of P just is df dx evaluated at the point P. And in future, when we go to higher dimensions, we're going to be using the partial derivatives. So partial f, partial x evaluated at the point P. Anyway, that's where we're heading. So just think of this straight line here as an excellent approximation to the blue curve f of x at this one point and for a small range of values around that point. And that's going to help us in getting, believe it or not, vectors from one manifold to another. And you'll see how shortly. All right, so let's consider R2 now. Let's go to two dimensions. So F is a map from R2 to R2. So we're just talking about Euclidean, two-dimensional Euclidean space to two-dimensional Euclidean space. Here, X now is going to be the column vector X1, X2. I mean, I could have put X and Y here. X1 is X and X2 is Y. You can think of it that way if you wish. Point P here is P1, P2 because we're now in two dimensions here. And this is a column vector here. So for a function f of x, remember that blue line, this now in two dimensions, so we're now going to have a surface. We're going to have a column vector here, f1 of x1, x2, and second coordinate function f2 of x1 and x2, or x and y if you want. Now the Jacobian matrix, df evaluated at the point P, at a point P is df of P, so the Jacobian matrix evaluated at the point P, because remember we had to have the point P where the fit to f of x is excellent, very good. Okay, what are the terms in this matrix? Well, you can see there's two coordinate functions here of two variables. So we're going to have df1, dx1 evaluated P, df1, dx2 evaluated P, and then we're going to have df2, dx1 evaluated P, and when I say d, I should say partial f2, partial x2 evaluated at P. Okay, the first order approximation of f around the point is f of x is approximately df of P dot x minus P, and where these now are vectors. df of P is a matrix, in this case 2 by 2, and f of P is a column vector, x minus P is also a column vector, so writing that out, f of x is approximately, here's our Jacobian from above, x1 minus P1, x2 minus P2, f1 of P, f2 of P, and remember there's two coordinate functions. If you want, you could have x minus P1 and y minus P2, it's up to you. Now, so here's our manifold N, the second manifold. Here's f of P, our point, and we have, this is the tangent space to the manifold N at the point f of P. Remember, under the map, we took P on manifold M and mapped it to f of P on manifold N. So we have d f of p, this vector here is d f of p x minus p, just like in the one-dimensional case. This is now a two-dimensional case. All right? In case of one variable, this is now in the case of two variables here. So we have this vector now, and f of x is approximately df of p dot x minus p, the matrix times the column vector x minus p, plus f of p is this object here, as we saw earlier. All right, so the Jacobian matrix df of p provides a linear approximation of the map f from M to N, because remember the derivative of f at p gave us that beautiful fit with f of x, as we saw in the one-dimensional case. So near the point P, it encapsulates how f changes locally by describing the rate of change of each output coordinate function of f with respect to each input coordinate direction. So partial f1 over partial x1, partial f1 over partial x2. All right, remember there's two dimensions in this case, and of course higher for higher dimensions. So in local coordinates, the entries of the Jacobian matrix df of p are the partial derivatives, partial f of j over partial x of I, and these partial derivatives measure the rate of change of the component functions fj with respect to the coordinates xi in each of the separate directions. So when I is 1, you have in the x direction. When I is 2, you have in the y direction. When I is 3, you have in the z direction, and so on, if you want to think of it that way. All right, since partial derivatives are inherently tied to changes along coordinate directions, which are represented by basis vectors of the tangent space, partial x1, partial x2, etc., the Jacobian matrix is naturally defined in terms of these tangent vectors. All right, so they're tangent vectors. So this object does exist in the tangent space, not on the manifold, not in the manifold, but in the tangent space to the manifold at each point where vectors live. All the vectors exist in the tangent space. So a local linear approximation to the Jacobian matrix df of p at a point P belongs to M gives a local linear approximation of the map F near P, as we saw earlier in the good old high school case y equals mx plus c at the point P. It tells us how small changes in M around P are mapped to changes in N around f of P. Because remember how this df of P gave us a good fit, to f at a point P, but only at a point P, not everywhere, not globally. So the Jacobian matrix df of P is essentially a linear transformation between the tangent spaces TPM and Tf of Pn. It maps each tangent vector in the tangent space to M at the point P to a tangent vector in the tangent space to N at the point f of P. For each point P belongs to M, the Jacobian matrix df of P defines the push forward, and that's given the symbol f star P, right, the star being the push forward, and at the point P, under the map F, from the tangent space TPM to the tangent space Tf of P of N. So f star of P is equal to df of P is a map from TPM to Tf of Pn. Now, push forward is a linear map, so the push forward f star P is a linear map that applies the Jacobian matrix df of P to tangent vectors at P to obtain tangent vectors at f of P. All right. So the push forward vector of the vector x minus p, as we saw earlier, remember x minus p in the one-dimensional case, now became x1 minus p1, x2 minus p2, the 2 by 1 column vector that we saw in the two-dimensional case, belongs to TPM is the vector df of p dot x minus p belongs to tf of pn. This is the general case, and of course in the diagrams I'm just showing you the two-dimensional case. So here's our the f star of P, and here's the vector we are pushing forward from the tangent space to M at P to the tangent space of N at F of P. So here we are, here's P, the point P here. Here's our vector x minus P, and we're going to push that forward to this tangent space here, okay? The tangent space to N at the point F of P, at the point F of P, yes. There's F of P marked there on the manifold N. df of P times dotted with x minus p, so that's the matrix times the column vector. All right, and also we can say f star p x minus p is also df of p times x minus p, so the matrix times the column vector. They're two different ways of saying the same thing. In this notation, f star p or df of p, it's the same thing, okay? And then you put the vector in front of it that you want to push forward. All right, so that's how that's working. So I can't emphasize enough, if you go back to that first one-dimensional example, the high school gradient thing, where df of p was used to approximate the curve f of p at the point p, the curve f of x at the point p. So how do we push forward any given vector vp? So rather than just x minus p now, we're just going to talk about any vector in the tangent space, electric field vector, magnetic field vector, some other velocity vector in some tangent space on some manifold, particularly in general relativity there. We want to push that forward to another manifold. All right, how do we do that? So we go from f of x is approximately df of p dot x minus p, which is an excellent fit around the point p, plus f of p. So in 2 dimensions, here's what it looks like. To f of x is d f of p dot vp plus f of p. So remember how we did this earlier? Well, instead of pushing forward the vector x minus p, we're going to push forward some other vector, random vector, whatever it is, v subscript p. Now the v is the vector we're interested in, whatever it is, electric field, magnetic field, whatever the question is, at the point p. The subscript p meaning at the point p. It's just further reinforcing what we're saying. So remember this approximation to this f of x is only as good as we are close to the point P. Okay, it's not it's not globally true, this. So f of x is partial f1, partial x1, blah, 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 and this time v1, v2 instead of x1 minus p1, x2 minus p2, plus f1 of p, f2 of p. All right, let's keep going. All right, now this transformation applies to all vectors in the tangent space, all vectors. Take any vector you want, push it forward from one manifold to another. So push forward in local coordinates. Suppose x1, x2, xm are local coordinates on M around P, and y2, that meant to be y1, y2, yn. There should be a y1 there. Sorry about that. I missed that in the proofreading. Whoops, painful. That's y1, people. Then y2 up to yn. Are local coordinates on N around f of P. Dimension of M is a dimension of the manifold M is little m. Dimension of the manifold y or n, sorry, manifold n is n. All right, so in these coordinates, the map f from m to n can be written in terms of its component functions, fj, x1, x2, xm. Now that's quite wieldy. So we just label them yj, where j starts at 1, should have been a 1 up here, 2 up to n. Now, a tangent vector v that belongs to the tangent space of the manifold M at point P can be expressed in local coordinates as v equals vi partial xi. These are the basis vectors evaluated at the point P. Remember, we're interested in the point P. These vectors are attached to the point P. Now, the push forward f star of P of v, f star P at P of v, star being the push forward, f subscript the star here indicating the push forward under the map f at the point P of v in local coordinates is then f star P of v is vi partial fj partial xi. Remember the partial over partial xi is this one here, and fj are the coordinate functions it's acting on, or the component functions here it's acting on, and then expanded in the basis on the manifold n, and the basis for the manifold n is the basis vectors partial yi evaluated f of p. Remember, this is evaluated P, this is evaluated f of P. These are the basis vectors on manifold N, and these are the components on M. Right? Now, F here is from M to N, so this is the output here. So we're doing these, into which we substitute the coordinates from manifold M to get the components on the manifold N. All right? Because remember, we have this map from M to N. All right, so I hope that's clear. Talking away with words there. All right, so here, partial fj over partial xi evaluated at P are the components of the Jacobian matrix of F at P. This Jacobian matrix captures how F locally changes the coordinates from M to N. And partial yj evaluated at F of P are the basis vectors of the tangent space to the manifold N at the point F of P at the point F of P. So thus F star P of V applies the Jacobian matrix of F to the vector V to produce a vector in the tangent space of N at the point F of P. And that's the beauty of this. So geometric interpretation of this. So geometrically, F star P of V describes how the vector V, which points in a certain direction at the point P on the manifold M, gets pushed forward to a new vector at the point F of P on the manifold N. All right. Just a short note, when you look at this video later on, sometimes, you listen to me speak, but sometimes once you've heard that, maybe just turn off my voice and just go look through the notes themselves and just think about it a little bit, particularly that first example of one dimension, that sort of high school example of the gradient, how we fitted the curve f of x at a point P with a straight line. Anyway, let's come back here. So it captures how a small change or movement in M at P translates to a corresponding change in N at F of P. So df of P dot Vp, remember this will be a column vector and this will be a matrix, is a map from the tangent space to M at P to the tangent space to N at F of P. So here we are, point P, here's our vector, whatever it is, whatever it represents, in the tangent space of the manifold M at the point P, and under this map, we will take it over here, push it forward to this vector here, F star P of V, in the tangent space of the manifold N at the point F of P. All right? So F star P of V is one notation you can use, but it means the same thing as df of P dot Vp, either notation you can use to describe this push forward. All right, so an example of push forward, let's consider an example where M equals R2, M is R2 and N is R2, they're both the same Euclidean space, two-dimensional Euclidean space, and the map F from R2 to R2 is given by f of xy is x squared minus y squared, and 2xy, that's the x component, y component, and we consider now, we can write this as sigma 1 of xy, sigma 2 of xy, so xy is mapped to f1 of xy, f2 of xy, which we can just simplify when we start writing out the basis vectors to mean just sigma 1 and sigma 2. So if we take a point P equals 1, 1 in R2, so that f of 1, 1, when we substitute that in there, so we put 1 in here and 1 in here, 1 squared is 1, minus 1 squared is 1, that's 0, and 2 times 1 is 2, so we get 0, 2, and a vector V that we're going to push forward, we're going to push forward a simple basis vector, partial x. We want to push that forward from M to N, from the manifold M to the manifold N. So what's going to come out in the tangent space to the manifold N at the point F of P? What are we going to get? Okay, so point P is 1, 1, so partial x, so this is the basis in the x direction, a basis vector. Then the push forward of V under F is 1. First we compute the Jacobian matrix of F, df. Here's the Jacobian, partial F1, partial X1. X1 is just X, sorry about that. Partial F1, partial X2. X2 is just Y, so partial F1, partial Y. And when we do that, we take the derivative of this, F1, with respect to X. So we get just 2X. And the partial derivative of F1 with respect to X2, which is Y. Okay, we're going to get minus 2y. And then down here, 2y and 2x are these partial derivatives. And so we've got the Jacobian acting on F. Now we evaluate the Jacobian at the point P 1, 1. So x is 1, y is 1. Well, that just becomes 2 minus 2, 2, 2 at the point 1, 1. Remember that point P is important. Then, next step, apply the push forward to V, which is partial x. So remember that basis vector in the x direction at 1, 1, which is just in component 1, 0 component form. So F star P of V, I've chosen to write out the components, so VI. Now remember V1 is 1, V2 is 0. So VI partial fj, partial xi, and then expand in the basis partial sigma j at f of p. All right, so putting all those in, what we're now going to have is where the v is. I'm going to put this vector in there. Okay, so it's just writing out. And we have v1, partial f1, partial x at 1, 1, and partial sigma 1 at f11. And we had f11, okay, which is a 0.02 on n. And then plus v1 partial f2 on partial x1. I wish I'd spaced that a little bit better. I wish I'd seen that in the proofreading too. And we have here 1, 1, and expand that in the other partial basis vector, partial sigma 2, evaluated f11. So we get f star 1, 1 is that is equal to v1 is 1 up here, you can see 1 times this is 2, that's this one here, so 1 times 2, and then expand that in the basis partial sigma 1 at 0, 2, f11 is 0, 2. And then here v1 is 1, remember v2 is 0, so it's not going to appear in these calculations. And we're going to have partial f2 partial x will be this one here, 2, and so at 1 times 2, evaluate 0, 2, so you can see what this is going to be. Next page over, this is equal to 2 partial sigma 1 at 0, 2, and plus 2 times partial sigma 2, the other basis vector, at 0, 2 on the manifold n. So this means the vector v equals 1, 0, component form at 1, 1, belongs to the tangent space to m at 1, 1. All right, is pushed forward to become the vector f star p of v equals 2, 2, 2, 2, is writing in component form, at 0, 2 is an element of the tangent space to n at the point f of p equals 0, 2. All right. Note that the tangent space T1, 1, M is attached to the manifold M at the point P equals 1, 1 on M only. Remember, it's that tangent space is connected to M at the point only. This is one thing I want to make out. Clear tangent spaces touch the manifold at a single point. We are then free to use this point as the origin of our coordinate system for the tangent space itself. I'm going to present a diagram in a minute. Likewise, the tangent space T to the manifold n at the point f of 0, 2, all right, that should be f of 1, 1 there. Sorry, that's an error. There should be no f there. It's tangent space to n at the point 0, 2 is attached to the manifold n at the point 0, 2 on n. Sorry about the f there, shouldn't be there. I missed that in the proofreading. All right, so here's a diagram representing what we've got. So here's our map f star of the point 1, 1 on M here, is a map from the tangent space to M at the point 1, 1 to the tangent space to the manifold N at the point 0, 2. It's better, so that's f of 1, 1 or 0, 2. So this vector 1, 0 at P becomes the vector 2, 2 at f of P equals 0, 2. Right. So this vector here, v, has been pushed forward to this vector here, f star 1, 1 of v. All right. I should probably put a little v in there. Okay, so down here we've gone from v equals 1, 0, 1, 1 under the map 2, under the map f, to f star 1, 1 of v is 2, 2 at 0, 2. All right. Now, p equals 1, 1 on m. That's the point at which the tangent space connects to the manifold, but that's the point from which we can set our origin for the local coordinate system on this grid here. All right. So hence my vector, I choose this as the origin here, and we go 1 unit in the x direction, 0 in the y direction. All right. Same here, 0, 2 on n, but here, that point there where the tangent space touches the manifold n, the only point where it touches, that we can then take as our origin for our vector. Okay, so that's 0, 0 in the tangent space, and so a vector of 2, 2 is 2 units up, across, and 2 units up. Here's 2, 2. All right, so that's where we are, that's where we stand. And I think what I'm going to do is I think the next page there it was blank, so I'll just go back. All right, and we'll finish up there. Anyway, thank you for watching this. I hope this is useful to everyone. I hope you enjoyed it. And please, as I said, you've listened to my explanation. And maybe try running the video through again, but without my voice, and just read the notes for yourself and have a think. And particularly that bit where we've taken that analogy of one dimensions and the equation of a straight line, the red line being y equals mx plus c, of that form that we're all familiar with from secondary school, and using that to guide, to take us then up to 2 dimensions and beyond. All right. We need the map F between one manifold to another. Okay, so from M to N in this case. And it's the differentiability of that map that allows us to approximate F locally at a point, and to then take the derivative involving that point, okay, and that allows us to push vectors from one manifold tangent space to another manifold's tangent space. All right, thank you very much for watching. I hope you liked the video. I hope you found it useful. Please do subscribe and hit the like button for me if you will. I greatly appreciate that. And thank you all again, and I wish you a good day, and I'll see you in the next video. All right, thank you everyone. Take care. Bye.